All right, well, let's get to our algebra. I think everyone's here that's going to be here anyway. We've got a lot of folks here. Let's see. 12. We're missing just a couple folks. Hopefully, they'll wander their way in here. But let's go to Buzz and take a look and see what we have waiting for us. I know we started this unit before spring break, but we'll go to our grade screen as usual. Take a look at our stuff. See, we've already done all of that. We've done all the matrices. Before spring break, we had simplifying rational expressions and discontinuities. That means when we had a hole in a rational expression, or if we had a asymptote, we had vertical asymptotes that we were looking at, that was created a discontinuity where it doesn't continue, a hole or an asymptote. We're going to look more at asymptotes today and how to solve rational expressions. And then next week, we're done with the unit. This is a very short one. We did 1 week before the break, 1 week now, and then we'll have the test over this next week and move on to something else that'll, going to finish the year. We don't have much time left. We got like 9 weeks here, 8 weeks. Not much time, but we will get done what we can. But we're going to look at 6.03 and 6.04 today. So let's go over to our activity screen and see what it has. Matrix. I'm going to close the whole folder on matrices. We're done with that. So we should just have the module 6 folder open, and we're on 6.03 this week. All right. So when you were in elementary school, you learned about latitude and longitude. Probably don't remember much about that now, but you did. That's those imaginary lines, horizontal and vertical, that circle our globe. When you see a globe, you see those lines. It's not actually on the planet. We don't see those lines when we get in an airplane and look down at the ground. But there are those imaginary lines that we use. They may not have seemed important to you when you learned them in grade school because, elementary school, you probably didn't even really understand what you were learning. But now you can imagine how important these lines are to airline pilots. They are used to navigate and determine their locations in the sky. We have imaginary lines we use for a lot of things, actually. The borders of a city or a state. When you leave Arkansas and cross into Missouri, there's an imaginary line. We don't actually see it, but, if you're standing on Arkansas sideline or Missouri sideline, there's different laws. There's different police jurisdictions. Everything's different depending on which side of that imaginary line you're on. So that divides cities, states, countries, counties, all kinds of things. And while we may not be able to see these lines drawn on the ground, they are important. Like, consider a military pilot. Think about this. If a pilot was to cross from South Korea into North Korea over that imaginary lines, that could start the war back up. If North Korean government did not give them permission to cross that line, because that's a very unstable area of the world still today, 70 years after their war. They're just crazy over there. So imaginary lines that the graph of a function or equation approaches more and more closely, they're called asymptotes. Asymptotes. It's an imaginary line that the graph of a function approaches more and more closely, which is just what it said in that sentence. So it's kind of funny. They put a definition of it there. Let's take a look. All right, we're going to learn in what ways can we identify vertical and horizontal asymptotes. So let's go to page 2. All right, vertical asymptotes. If an asymptote is an imaginary line running alongside the graph of a rational function, then a vertical asymptote must be one of those imaginary lines which continues up and down forever. So let's take a look at this graph of 1 over x. This is the function 1 over x. We see there's 2 different pieces to the graph of 1 over x. A lot of rational functions have more than one piece. When we graph quadratic equations, it's a parabola and it's all connected. It's all one piece. Lines are all connected. A lot of things that we graph are all just one piece. They may make a lot of funny shapes, but there's just one piece to them. Rational functions can have many, many pieces, sometimes 2, sometimes more. And we can see that there's a vertical asymptote right there where the y-axis is. This graph of 1 over x does not touch the y-axis. it gets really, really close. The farther we go up or the farther we go down, it gets closer and closer and closer to pretty soon you're having to measure it with 10,000ths of a number. It's not even a tenth. It gets closer than a tenth. It gets a tenth, 100,000, 10,000. It gets really, 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 really close. And we can actually see that there's also a horizontal asymptote to this function because it doesn't touch the x-axis either. It gets really, really close, but this has a vertical and a horizontal. But we're going to focus on the vertical right now. Yeah, the asymptote is y equals 0 and x equals 0. That would be the graph, the line, that imaginary line. So there's a piece in the first quadrant and a piece in the third quadrant. Let's review the quadrants. We haven't talked about quadrants this year, and maybe a while since you've studied that. But the graph is divided into quadrants, just as a refresher. Quadrant 1 is like where the real world exists, right? All the positive numbers. X numbers are positive, the Y numbers are positive. That's why that's generally considered quadrant 1. Because when you have graphs and charts and stuff that show you things that are going on, it's usually in quadrant 1 because we're dealing with, times and values, and generally we're counting time as positive minutes and values as positive numbers. So we live in quadrant 1. The number of the quadrants goes counterclockwise. So if you start over here in quadrant 1, when we jump over here to the negative x values, that's quadrant 2, where the y's are still positive. Quadrant 3 is below that. And then, of course, quadrant 4 would be the last one on the right, on the bottom underneath quadrant 1. So just a refresher for your quadrants, because it's always good to go back and refresh ourselves. All right. It says, why does this happen? Talk about the different pieces. Since the variable in the denominator, there's a variable in the denominator, 1 over x. The value of the denominator changes as the variable changes, right? As the denominator of the fraction gets closer to 0, 1 divided by x, and as x gets closer to 0, that's being 1 divided by a very, very small number, the value of that fraction increases. 1 divided by a half is 2, but 1 divided by a fourth is 4, and 1 divided by an eighth, 0.125 is 8. If you divide it by 0.1, it's 10. So the smaller that x gets, the larger the value is going to get. 1/8, 1/4, 1/2. But the x can't be 0, right? We can't have 1 over 0 because that a fraction means divide. 1 divided by x. We cannot divide by 0 because that does not exist. That's an undefined fraction. So that's why it never touches. It'll never touch either of those asymptotes because it will never equal 0. 1 divided by 0 doesn't exist. So there's restrictions on that x. X can't be 0. So x, a lot of times with our x value or our domain, a lot of times that's equals any number. In this case, it can't be 0 just because it's on the bottom of a fraction. Let's go to page 3. It's 4 minutes, and then we'll make it larger where you can see this real well. Here we go.
We're going to look at how to find the asymptotes in a rational function, that is, one that's in the form of a ratio or a fraction. Now first we're going to find our horizontal asymptote. For that, all we need to look at is the degree of the numerator versus the degree of the denominator. And we have 3 cases that can occur. We can either have a higher degree on the top, an equal degree top and bottom, or a higher degree on the bottom. If we have a higher degree on the top, what happens is that highest degree term is going to grow the fastest of all the terms in the fraction. So the top of the fraction is going to grow larger faster than the bottom of the fraction. So as the top gets larger in relation to the bottom, the fraction is going to grow larger and larger and larger forever. So it's never going to approach any particular value. It's simply going to increase without bound. So there will be no horizontal asymptote if you have a larger degree on the top. If you have an equal degree top and bottom, our largest 2 terms, top and bottom, are going to sort of outgrow everything else in the fraction. And so our ratio is going to approach the ratio of those 2 terms. So our asymptote is the ratio of our 2 leading coefficients. Now, as we have in this case, the degree is higher on the bottom. So what's going to happen here? Well, the bottom of our fraction is going to grow larger faster than the top of the fraction. So in that case, the value of the fraction is going to get smaller and smaller. In fact, it's going to get teeny tiny after a while. It's going to begin to approach 0. So in this case, our horizontal asymptote is simply y equals 0 or the x-axis. Now what about our vertical asymptotes? Well, those are going to occur where there's discontinuities in the function. And those are generally where we have a 0 in the denominator. So let's factor this so we can see better what's going to happen. Well, this is the difference of two perfect squares, so it will factor easily into x plus 2 times x minus 2. Now, we might be tempted to say that we have horizontal asymptotes at both of the zeros that are going to occur here, both at x equals 2 and at x equals negative 2. But what I see here is that we have a common factor in the top. And this is going to cause something a little different to happen. You see, you get an asymptote where you have a 0 in the denominator and a number in the numerator. And so as you approach that point, as the denominator gets closer and closer to 0, our value increases rapidly. And so that's why we have that line swoop up alongside our asymptote going off towards infinity. But we're not going to have that happen here at x equals 2 because we have a common factor. The numerator and the denominator are both going to approach 0 at the same time. Or to look at it another way, the only value that will give us 0 for these two factors is exactly 2. If we put in 2.01, they won't give us 0. They'll simply give us 0.01 and 0.01, and they'll cancel. And they'll just leave 1 over x plus 2 to give us our value for the function. If we put in 1.99999, as many 9s as you want to go, we would not get 0 over 0. We'd get same number over same number. They will cancel. And they'll just leave us with whatever's happening with 1 over x plus 2. So in this case, we do not get a vertical asymptote. Instead, we get a hole, and that's going to occur at a value of x equals 2 because x minus 2 is a common factor top and bottom. Now, that leaves us with a factor of x plus 2 in the bottom, and that means at a value of x equals negative 2, the fraction will become undefined. We'll still have a number in the numerator, and so that gives us a vertical asymptote, and that is going to occur at x equals negative 2. Now, what about our domain? Well, for our domain, we have to take both these into account because they are both going to cause an undefined function, and so we can't have that occurring. So we need to leave both of those out. So our domain is going to be all reals except x is not equal to negative 2 or 2. And that's how we find the asymptotes and the domain of our rational function.
Okay, so he talked about both the horizontal and the vertical asymptotes and how we find those. And he kind of hit a little bit on the horizontal asymptotes. We're going to get into more of that. But we're going to go back and talk more about what he was saying with this equation. They said in order to find the vertical asymptotes, we'd have to figure out what numbers cannot be in the equation, which means, the denominator can never be a 0. Can never be 0 because when it's 0, it's undefined. That's going to tell us there's a vertical asymptote there generally. Now this equation, it's not x minus x. I was in a hurry there. X minus 2. X minus 2 over x squared minus 4. We need to factor that because as he pointed out, there's an x minus 2 on the top and the bottom. Well, that's going to cancel each other out because x minus 2 divided by x minus 2, that's just 1, right? It doesn't matter what the value of x is. You're going to have the same number on the top and bottom. So this does not change anything. It's just 1. So this is the same as 1 over x plus 2 because you got a 1 there, and this is, times a 1. 1 times 1. That doesn't change anything. Those cancel each other out. So 1 over x plus 2 means we can't have x equal to negative 2 or this equation be 0. And we can see that, yes. But what happened to this other one, x minus 2? It can't be x minus 2, so equal to 0. So x can't be 2 also. X can't be 2, x can't be negative 2. Because we can see that either one of those would create a problem. Because 2 squared or negative 2 squared would be 4, and that would make it a 0 on the bottom. But this one is not a vertical asymptote. This is a vertical asymptote. This is a hole, or like a hole. How do we know it's a hole? It's a hole because it exists on top and bottom. Now let's visually look at this as a graph so we can understand what do you mean by a hole. If you don't understand what it means that there's a hole there, let's go look at this. Let's open up Desmos. If you don't understand any of these equations, I always encourage you to go graph them on Desmos, because that helps a lot of times to be able to take a look at exactly what the graph of these functions are doing. We can graph either one. Let's go to x squared minus 4. It doesn't matter which way we graph it. It'll graph the same whether we write it as the factored version or the regular version. So let's take a look at this. There's that asymptote. He said there was an asymptote at x equals -2. I'll put the line so it's not invisible for us. There's that -2 vertical asymptote. We can see it gets closer and closer and closer. Farther up we go, it's getting really, really close up there. To eventually, Desmos doesn't even show a difference. Unless you zoom in. You start zooming in and you can see, yep, there's actually a gap between those two lines. But, you get far enough out, you can't even tell there's a gap between those lines anymore. But it's always there. And you can go up hundreds and hundreds and hundreds if you want. And zoom in far enough, you'll see it still never touches, even though it looks like it does. But we also said x cannot be +2. Well, if we look at Desmos, it sure looks like it could be +2. If we zoom in over here where it's 2, what do you mean it can't be 2? Look, it's there. I can see it. Well, don't be fooled. If you click on that graph, all right, here's the value of the graph where my mouse is. If I get this mouse over here to where it's 2, oh, it does not exist right there. Look, it changes it to a hole in the graph. It is not defined at 2. We said x cannot be 2 for this equation. So Desmos knows that, but if you don't click on it, you won't see it on Desmos. So it can fool you. So you need to be able to identify it by looking at the equation. The graph does not exist at exactly 2. It exists larger than 2, smaller than 2. Only exactly at 2 does this graph not exist. So that's the hole in the graph that we saw when we were looking at the equation. It's not so easy to see. If we were graphing it by hand, we would actually put a hollow circle there to show a hole in the graph at 2. But just because you look at a Desmos, don't be fooled by that. It does not exist when we have x equals 2. So yes, that's where that come from in his video talking about 2 and -2 are both discontinuities where the graph does not continue through those points. But one is a vertical asymptote and the other one is not. It's a hole. All right, so important note, if the denominator is a factor of the numerator, that's a discontinuity. That's what we were just talking about. That's a hole. If the same factor exists in the numerator and the denominator, that tells you there's a hole, or they call it a discontinuity. That's the same thing. It means it does not continue through that point. It stops, and then it starts again on the other side of that point. So it does not continue. It's a discontinuity. But no, when you see the word discontinuity, that means it's a hole. To simplify that in the terms that we're used to, it's a hole in the graph. All right, so they're looking at another one here. 3x squared divided by x. Well, on top, you have 3 times x times x. On bottom, you have x. So one of those x's cancel out. So that means it's really just the graph of 3x. It's going to look like a line, except for there's a hole where x equals 0. We can look at that real quick. Let's get rid of this one. 3x squared divided by x. It looks just like the graph of 3x. Just a straight line, even though it's a x squared equation. But it said that there's a discontinuity. There's a hole at 0. Yep, there it is. It's not defined. So this is actually two separate graphs because there's a hole. It doesn't continue through the 0. So just pay attention to that when you're working on these things. Okay, so now it gives us another equation. Identify the vertical asymptote of 4 over x plus 3. 4 over x plus 3. All we have to do is figure out what x cannot be. What would create a problem? What would create a 0 in the denominator? Well, if the denominator is x plus 3, that means x cannot be negative 3. So there's a vertical asymptote there. So if you want to look at that, let's say on the graph, 4 divided by, see, what was it? Plus 3, x plus 3, x plus 3. There's the graph of 4 over x plus 3. And look, it's got two pieces like a lot of these do. And there is a vertical asymptote at x equals negative 3. Does not touch negative 3. Discontinuity. All right. If you have something like an x squared or something in the numerator or denominator, you have to factor it to figure it out. You have to factor it first to see, does the same factor exist in the numerator and denominator to know whether is this a whole or is this an asymptote. This one, you have an x minus 9 in the numerator, and the denominator factors to be x plus 1 times x minus 2. So you do not have a common factor. There's no repeating factor in the numerator and denominator. So you have two asymptotes, one at negative 1 and one at 2. Now, this actually makes a rather interesting graph. I talked about how it could be more than one piece. Let's put this there. F of x equals, and this was x minus 9. Put that in parentheses so it groups it all together. And on the bottom was x squared minus x minus 2. I think that was what it was. Yeah, x squared minus x minus 2. See, this is actually a 3-piece graph. But those asymptotes still exist. So there's an asymptote at x equals negative 1. And there was another asymptote at x equals 2. I can turn those off where you can see that. But this gets closer and closer to negative 1 as it goes down. It also gets closer and closer to 2 as it goes down. And up here, this is squeezed between both the asymptotes. It's getting close to 1 on this side. It's a negative 1 on this side. It's getting close to positive 2 on that side. So it's 3 pieces for that radical function. All right. And there's more examples. If you want to see more examples of it, you can click on that link and it will show you another problem to work. But let's look at page 4. Let's see. Now this talks about the horizontal asymptotes. All right, so I want to do this on paper here. Let's go through this together. I'm going to get rid of this one. This is great for your notes. Great to have this written down until you have it kind of memorized. Horizontal asymptotes. They work a little differently. So I tried to write this kind of neatly, but, you know, it just depends on the day how neatly I can write. So to figure out the degree of the horizontal asymptote, there's 3 different cases. Either the degree of the numerator is less than the degree of the denominator, or the degree of the numerator equals the degree of the denominator, or the degree of the numerator is greater than the degree of the denominator. So to understand even what we're talking about, we have to refresh our memory on what does it mean to have the degree of a function. So let's refresh our memories on that. Let's look at this function here. What degree function is this? Do you remember degrees? The degree of a function? F of x equals 2x squared minus x plus 7. Now we know that's a quadratic equation, but the degree of a function is the largest exponent. Largest exponent. We have an exponent of 2. We have there's actually an exponent of 1 there. We just don't write it when it's a 1. So this is a second degree. That's a second degree equation because the largest exponent is a 2. All right. What about this one? 5x squared. 3x to the 5th, pardon me, 3x to the 5th minus 4x to the 3rd plus x plus 33. All right, put the degree of that in the chat there. What is the degree of that one? I'm going to block this bottom. We're talking about the bottom. We're talking about that one right there, right above the highlighter. Elijah's got it. He's on top of it. Anyone else agree with Elijah? 3x to the 5th minus 4x to the 3rd plus x plus 33. What degree function is that? It's also a good chance to see who's left my class. The computer may still be in class, but they're not. Bethany agrees. This is a 5th degree because the largest exponent is a 5. All right, what about the one at the bottom there? Bethany says it's a 6th degree. Is it? Elijah says it's an 8th degree. Oh, now we need someone to break the tie. Oh, the rest of y'all are going to struggle on this assignment. Y'all are not paying attention. You're on your phone. You're watching Netflix. Jonathan's not sure. All right. Thank you, Jonathan. I appreciate that. It all gets down to, is it the first exponent or is it the largest exponent? The degree of a function is based on its largest exponent because this is not written in standard form. If I wrote it in standard form, I would rearrange it and put this one first because it is the largest. In standard form, you write it from largest to smallest exponent. This one was x to the 5th, and then x to the 3rd, and then x to the 1st, and x to the 0. 33 is actually x to the 0 if we want to look at it in terms of degrees. So just because it's not written in standard form does not change the degree. This is an 8th degree because 8 is the largest exponent in the equation. Okay, so now that we understand degrees a little better, had a little refresher on that, that helps us understand what we're talking about up here. If the degree of the numerator is less than the degree of the denominator. So let me see, I have some examples down here. I'm going to number these. Tell me which one of these is the degree of the numerator less than the degree of the denominator? Is it function 1, function 2, or function 3? Degree of the numerator is less than the degree of the denominator. This is a good refresher on which is the numerator, which is the denominator as well. 1, 2, or 3? Which one of those is the degree of the numerator less than the degree of the denominator? Well, there's a lot of people sleeping in this class. Okay, got people think it's number 2? 2? Well, 2 seems to be the common answer. Yeah, the degree here is 2. The degree there is 3. So yes, the numerator has a smaller degree than the denominator. So in this case, the horizontal asymptote, I'm just going to abbreviate that. Horizontal asymptote for this one will be y equals 0. Y equals 0. So anytime that the degree of the numerator is smaller than the degree of the denominator, it's y equals 0. It's the x-axis. It never touches it. Anytime. Degree of numerator, degree of denominator. Let's look at an example of that. Let's see. The one that we already had in place here. This is a first degree numerator, a second degree denominator. And look, there is a horizontal asymptote at y equals 0. See that? It gets closer and closer. There is a horizontal asymptote at y equals 0. Now on this side, it does something a little weird. It actually goes above it on the right side, but then it comes down and gets closer and closer and closer. It starts below it, actually crosses the asymptote on the right side. Right there, somewhere right around there. Yeah, see, it goes from negative to a positive. But then it starts approaching it from the top. It's really weird. But this side is an asymptote. It never touches it. Let's change this. Let's change the top to be x to the 5th. And the bottom to be x to the 8th. Still, we've got that asymptote at y equals 0. Let's just change it to x divided by x squared. There's the asymptote at y equals 0. It does not matter what the degrees are, but if this one's smaller than that one, it's always going to have an asymptote at y equals 0. All right, let's talk about the other case. If it's larger, like this one here, the top, the numerator, has a 5th degree. The denominator has a 2nd degree. In that case, none. There is not. It does not exist. There will not be a horizontal asymptote. We can illustrate that. Let's take a look. Let's change the top to be x to the 3rd now. Now the numerator is larger. Now look, there's no asymptote. That's just a straight line, actually. Let's make it x to the 5th. 5th. How about that? See, there's no asymptote. Let's change the bottom to be the 4th. Back to a straight line. 3rd. Plus x. Anytime the top is larger, there's not going to be an asymptote. X squared. X squared. It'll do all kinds of wild different things, perhaps. See, look at that graph there. That's really wild. It's got all kinds of things going on, but there's no horizontal asymptote. 5x to the 5th over 3x squared plus x minus 8. It's got all kinds of things, but there's no horizontal asymptote because the numerator has a larger degree. So let's look at the last case. The last case is the only place that it changes because this is always true. It's always y equals 0. This one's always true. There's never one. But if the degree of the numerator equals the degree of the denominator, it is the fraction created by the coefficients. Of the largest exponents. You're like, what? The fraction created by the coefficients of the largest exponents. Okay, we need an example, Mr. Brock, because you're going to confuse us. All right. So this one here, look, this is a 4, 4. Those are both fourth degree functions, right? Both of these are fourth degree. That's the largest exponent. So this does not apply, and this does not apply because they're the same. So it does have a horizontal asymptote. It's not at y equals 0. It is at y equals 3/5. Where'd I get that? That is the coefficients of the fourth degree terms. I just take the coefficients. I simplify it if I need to. If that was 3/6, it'd just be a half. You know, if it was 10/5, it'd be 2. But it's 3/5. So let's look at that on decimals. Let's say we've got f of x equals 3x to the fourth. And I'm just going to do 3x to the fourth divided by 5x to the fourth. 5x to the fourth. All the rest of that, oh, I guess we need something up there. Otherwise, it just makes a line. Okay, minus 2x squared. And then minus x. And then the bottom was what? 5x to the fourth plus 3x to the third minus 1. Wow, it really makes a wild graph. Stuff happening everywhere. In fact, there's even a piece that just goes like a third degree through there. But there does seem to be some kind of asymptote happening because this is approaching a line. It's closer and closer. We said it's y equals 3/5, which is 0.6, right? Y equals 0.6. See, this is getting it thinks it is 0.6 until we zoom in. Then we can see there's a difference. It's very, very close to 0.6, but that's the asymptote for part of the graph. Notice not all of the graph behaves that way. This would actually, this middle section crosses over. But there is a horizontal asymptote at 3/5. So this is good for your notes, and it's probably good to have an example, such as having the 3/5. Now, this is also in our lesson. If you want to get a cleaner notes, not having to copy mine, here it is, the relationship between the degrees of the numerator and the degree of the denominator. The degree of the numerator is smaller. Horizontal asymptote y equals 0. It's greater. There's no horizontal asymptote. They're the same. You just take the leading coefficient numerator and put it over the leading coefficient denominator as a fraction. All right, this is identify the horizontal asymptote. 3x plus 8 over 2x minus 5. In that case, I won't play the whole video there. I'm just showing it to you. You can watch the video. It's like 35 seconds or something like that. The horizontal asymptote, we look at the degrees. Well, that's a first degree equation over a first degree equation. So if they're both the same, they're both first degree equations, the asymptote must be at y equals 3/2. We just make that fraction out of the coefficients, 3/2. And in the video, when they get to the end, make it big enough to see. Oh, it's hidden behind there. 3/2. There it is. See, they're taking the 3 and the 2 and making 3/2. So that is the coefficient. Lesson summary right here on page 4. Asymptotes. Talks about vertical asymptotes, horizontal asymptotes. You find the vertical asymptote by setting the denominator equal to 0 and solving for x. And it says of the simplified function, which means if you have x plus 2 over x plus 2, numerator and denominator, those cancel out and do not count for the vertical asymptote. You have to simplify it. And that'll give you the asymptote. Remember, that's a hole. That's not an asymptote. And then the horizontal asymptote has this chart again here in the summary. So that's how we find the asymptotes. Again, this is only page 4, so it has 2 pages of practice problems for you in Buzz that you can go through to make sure you understand. So this one has 2 different tabs, 3 questions on each tab. Identify the vertical asymptote, 3 over x. Well, in that case, it's just x equals 0, right? 3 doesn't make a difference. Excellent. Then you can go to the next problem. This one just gives you the graph. All right. And then there's more problems there. There's another page of problems over here. Page 6. Activity 1 and activity 2. Again, 2 different screens to go between. This one's matching, if you know which is which. In which case, does y equal 0, no horizontal asymptote, or it's the leading coefficient. Activity 2, describe the vertical and horizontal asymptotes. Do you know them both? And you can click there and it'll give you the answers. All right, let's look at the assignment that goes with this first lesson. I think it's just 5 questions. It is. It's just 5 questions. Which equation represents the vertical asymptote? Identify the vertical asymptotes. Identify the vertical asymptotes. Identify the horizontal asymptote and the horizontal. So you got 2 to find the horizontal asymptote, 2 to find the vertical asymptote, and 1 to give the equation for vertical asymptote. All right, I'm going to get out of that. We're going to look at our second lesson, and we'll be done for the day. Now let's see how to solve rational equations. It's great. We've talked about asymptotes and all these other things about rational equations, but how do we actually solve it? And we're going to look at this little video of these 2 brothers painting their room. Make it big, make it bigger. It's only a minute 24.
Tom and Huck's family just moved into a new home. Tom and Huck each got their own bedroom in the basement, along with a shared area in between. All 3 rooms, the 2 bedrooms, and the shared area, are the exact same size. Tom paints his room blue to match his comforter. It takes him 2 hours. Huck paints his room green to match his laptop. It takes him 3 hours. They decide to paint the shared room together, but how long will it take? It must take less than 2 hours because Tom can do it alone in 2 hours, but Huck is helping him. You can solve the problem by first thinking about what happens in just 1 hour. In 1 hour, Tom can paint half the room because it would take him 2 hours to paint it all. Similarly, in just 1 hour, Huck can paint 1/3 of the room, but you don't know how many hours it will take with them working together, so call the number of hours X. If you add the amount of work that each of them can do separately in an hour, you find the proportion of the room that they can paint in 1 hour. So you can write 1/2 plus 1/3 equals 1 over x. Because this equation has an unknown in the denominator, it is a rational equation. Do you know how to solve it?
Well, not yet necessarily, but we'll get there. Oh, I like this little quiz they have on page 1. This is a very short lesson, by the way, because this just seems like it's way too easy. What number goes in this box? Type the missing number in each box complete. So what number would we put here? Blank over 2 equals 3 over 2. You're like, that's a trick question, right, Mr. Brock? Blank over 2 equals 3 over 2. Is it 7? 7 over 2 equals 3? No. It's not a trick question. 3 over 2 equals 3 over 2. That's right. Elijah was not going to be tricked. He was not. It is that simple on this little quiz thing here they put on page 1. I love it. Here's another one. What over 7 equals 9 over 7? This is just the beginning questions to make sure you're actually awake and functioning, because yes, 9 over 7 equals 9 over 7. But now they do get a little trickier. Yes, 9/7 equals 9/7. Nothing else would work. Now this gets a little trickier. Blank 17ths plus 1/17 equals 8/17. Do you remember how to add fractions? If you have the same denominator, you just add the numerators. You can totally ignore the 17s because they're all the same. So you can totally ignore them. So blank plus 1 equals 8. Elijah's not going to be fooled. Yes, 7/17 plus 1/17 equals 8/17. So it is a good refresher to remember how adding fractions work and subtracting fractions. You have to have the same denominator. Blank sixth minus 1/6 equals 2/6. They all have the same denominator. So it is 3/6. Job, Jonathan. 3/6 minus 1/6 is 2/6. That's just a refresher because when solving rational equations, we have to have the same denominator if we're doing something like that. So, yeah. So it says you can just do x plus 1 equals 8 because they have the same denominators. All right, let's look at this. We're going to learn what reasons justify a solution and how do they apply in the real world. So a rational expression is just a definition here. It's fractions that have a polynomial in the numerator and denominator. 5x plus 35 over 5x, or x squared plus 6x minus 27 over x plus 9. Rational equations, if it has the word equation, there has to be an equal sign. And they have rational items like 8 over x. There's got to be an x in the denominator to be a rational equation. But the word equation means there's an equals. Equal, equate, equations. All right. So, let's work this together. I'm going to work this one just to kind of refresh how we do this. Okay, so when we are finding a solution to a rational equation, we have to have the same denominator. So what would the common denominator be between x and 4? Well, 4x would be the common denominator, right? That includes both. So on this side, we have to multiply by 4 over 4. On this side, we have to multiply by x over x. Now, what are we multiplying by? We're multiplying by 1. Right? 4 over 4 is 1. X over x is 1, regardless of what x is, unless it's 0. But we're not talking about it at 0 because it can't be 0. It's in the denominator. So this just multiplies by 1. So this is legal mathematically, right? We can multiply anything by 1, and we multiply into both sides by the same thing. We're multiplying both sides by 1. So when we do that, now we've got 8 over 4x. And over here, we've got 3x over 4x. Okay. This is great. If these are equal to each other, because it says right there, they're equal to each other. To solve this, we would cross multiply, right? 4x times 3x is be 12x squared. 8 times 4x, now it equals 32x. So far, not bad. If two fractions are equal to each other, it's legal to cross multiply. Can't do it just any time, but if they're equal to each other. So now we want to solve this. This is a quadratic equation, right? We got that. We need to move everything to one side. So we got 12x squared minus 32x equals 0. So we factor it. See what factors we can get out of there. Well, there is a 2 for sure, and that may be it. And there's an x. Both of those terms have an x. If we pull 2x out of there, that leaves us with a 6x. Oh, we can pull a 4 out of there. Yeah. How about a 4? That's better. 4 out of 12 is 3x. That's as small as it gets. And if we pull 4x out of 32x, it's 8. Okay, so we factored out a 4x. This is as small as it gets. It can't be factored anymore. So to find the solutions, we take each of these. If this is 0, then the multiply these together is 0. If this is 0, multiplying those together equals 0. So one of those or both of those could be a 0. So 4x equals 0. 3x minus 8 equals 0. So the two solutions we get when we divide by 4, x equals 0 plus 8. 3x equals 8. X equals 8/3. Quadratic equation. We expected to get two solutions, right? With the quadratic equation, you always generally get two solutions. But here is where radical equations can mess you up. If we have two solutions, we need to go back to the original equation, 2 over x equals 3/4, and test them. Let's take our first solution. 2 over 0 equals 3 over 4. Wait a minute, there's a problem there. 2 over 0 does not equal 3/4 because 2 over 0 doesn't even exist. We have to throw this out. This is an extraneous solution. Extraneous solution. It is a solution. The math works. It is a solution to this problem. But with the original equation, it doesn't work. It's an extraneous solution. So you will get some solutions that you have to throw out because for the original equation, it's not true. How about this one? 2 over 8/3 equals 3/4. Like, wait a minute, a fraction under a fraction? We have to get rid of a fraction under a fraction. So to get rid of 3/8, you have to multiply, 8/3. 8/3. I'm sorry, it was right. It was 8/3, so I'm going by 3/8. So we're multiplying by 3/8 over 3/8, which is just 1. But this now, 8/3 times 3/8 is 24 over 24 or 1. So that gets rid of the bottom because anything over 1 is just 1. So that means 2 times 3 is 6/8. 2 times 3/8 is 6/8. So this simplifies to 6/8. And 6/8 does equal 3/4. So this is a good solution. Because when we turn that over, multiply by 3/8, it simplifies to 6/8, which 6/8 is 3/4. So you have to check because a lot of times you will get an extraneous solution when you are solving any kind of radical expression. And this has the steps. If you click this little arrow here, it says multiply by 4 over 4, x over x. So that gets where we were there. Then they cross multiplied to get what we got, the 32x equals 12x squared. Then they set it equal to 0. Factored out the 4x like we did to come up with their two solutions, x equals 0, x equals 8/3. Substitute the 0 in. It doesn't work. It's an extraneous solution. That's a solution to an equation that does not fit the requirements of the original equation. So we throw that one out. And then they test the second one. And they just jumped straight from 2 over 8/3 to 6/8. I did the steps in between. But 2 divided by 8/3 is 6/8. And it does equal us. So it's confirmed solution. All right. I think this is the last page of the lesson. There's only 4 pages total. So here is a couple of word problems. And then the lesson summary is right there. So like I say, that's the end of the lesson. Find the common denominator, simplify it, solve for the variable, and then check to see if you got to throw any of those out. Because you got to reject anything that would make the denominator equal to 0. All right, so I'm going to work one of these with you. It does have how to do it underneath each of these little tabs. But let's work this one together, and I'll show you how do we solve a rational equation when we just have this word problem. So the math club at school is 70% girls. Okay. So the first thing you do is say, okay, we're going to say X will be the number of boys. And the girls would be 2 times the boys plus 5. Because that's what it told us. There's 5 more than twice the number of boys. And 70% girls, which means there's 30% boys in the math club. Then we have to set up the equation. So we can do that. Let's do it like this. So if X equals the boys, X would equal 30% on top. So 30. I'll just put the 30. We don't need the percent. X over 2X plus 5. It's the ratio of boys to girls. The ratio of boys to girls is 30 to 70. And the boys is X and the girls is 2X plus 5. Then it wants us to solve that. Well, we can cross multiply. Since they're equal to each other, it only works when they're equal to each other. So 70X equals 30 times 2X plus 5. All right, and we can simplify that. So 70X equals, let's distribute that, 30X plus 150. Move this over. Oh, that's 60. I did that wrong. 30 times 2. There's a 2 there. 60X. Subtract 60X. So 10X equals 150. So X equals 15. So when we solved it, X equals 15. Does that work? Well, X was the boys. So 15 boys. And the girls were 2X plus 5. So 2 times 15 plus 5. 2 times 15 is 30 plus 5. 35 girls. Girls. I don't need a T. Okay. Is that 70% to 30%? Add those together, there's 50. 50 times 70% is 35. 50 times 30% is 15. So when we check it, those work out. Let's see how they did it. X, 2X plus 5, 70%, 30%. They set up the X over 2X plus 5. And then, let's see, multiply both. They did the common denominator, but they canceled out the common denominator to end up with the same thing I did. Because they multiplied by the whole denominator. 70 times 2X plus 5. But the 2X plus 5s cancel out. 70 times 2X, and the 70s cancel out. So they basically cross multiplied. It's the same thing as multiplying both sides by the denominator. 70X equals 60X plus 50. 10X, X equals 15. All right. There's practice problems. There's another example you can go through. So you can try that yourself on paper and then check their example to see if you did the same. All right. I want you to solve 6 over X equals 10 over 15. And then you can check your answer. 3 problems there. 1 over 2X minus 1 equals 3/9. Check your answer. There's a second there. Create a rational expression. In the aquarium, 90% of the fish are blue. The rest are red. The blue are 10 more than twice the number of red. Can you set up an equation to solve? That's the tricky part, setting up the equation. There's the equation. And there's 2 of those for you to try. And there's the equation. All right. That's the last, because the page 4 just says, read the lesson, do the essential questions. All right, so let's look at the assignment that goes with this one. Start. Choose the equation that goes with this problem. So it gives you a word problem, and you have to figure out which one of those equations is how to set it up. Here's when you solve for X. Here's when you solve for X. Here's when you solve for X. And this one is another problem to set up, and you actually have to work the problem here. So this one you're setting up and working. 5 problems. 5 problems. All right, guys. Vertical asymptotes, horizontal asymptotes, and how to solve the problems. And then next week, we're going to test on rationals. So we're going to be done with it really quick. Really quick. And then we'll start something else in 2 weeks. So this week, it's an A-Day Friday. So we do not have class on Friday. We will only have class on Thursday. So if you want to work on this before Thursday, that's great. So if you have problems, you can come to class Thursday and say, Mr. Brock, I don't get it. Can you help me? Absolutely. If your grade is below 70%, then you have to come Thursday. I will see you Thursday. But otherwise, if you don't need help and your grade's over 70%, I'll see you in April, because that's next Tuesday. We'll be in April by next week. So, all right, guys, I'm going to let you go. Have a great rest of your day. I do have the grades updated for your grade checks and advisory. So have a good one.